Hi, everybody. Happy Asynchronous Friday. Hey, we still need to wrap up lesson 3.7a, your student activity sheet. So I thought I'd just make a quick video, help you get through it, and you can submit it all at one time. It's due by midnight tonight. I am sitting on, actually, I could go, well, I'm just sitting on our announcement for today. It's for Friday, April 9th. It says to complete your lesson 3.7 student activity sheet, click on this link to our page for the day. The page has a link to a video that I made to help you finish the activity sheet and get it submitted due by midnight tonight. So I'm going to go ahead and click on that. It'll take us to our April 9 asynchronous lesson. So this is where you're going to watch the video, and hopefully you already figured that out. Okay, it says, it's got our learning target here, but then I also wanted to scooch and read the section that says first making it real. We have been working with a computer simulation actually over several lessons. Even in our last unit, we were working with a computer simulation to test our hypotheses and our predictions about the impact of different variables on the buffalo and wildebeest populations in the Serengeti. So here's my question to you. Do scientists really use simulations in their research, or is that just something we're doing in the high school? Can any of you think of a recent situation where scientists were using computer simulations to add evidence to their claims? Give you one guess. Why have they been using computer simulations recently? Okay, for coronavirus, you guys, they're using computer simulations all the time. It would be unethical for scientists to actually do human research where they inject people with coronavirus and then watch how it spreads from one person to the next. So they're using computer models to figure out how it's going to spread and when we should expect the cases to rise or to decrease, that kind of thing. So I just wanted to show you really quick. I just did some quick research where I just asked about computer models and coronavirus, and these are the things that I pulled up. I'm not going to spend long. I just wanted to show you. Scientists use computer simulations to identify future targets for treatment of COVID-19. So it says here, scientists use the simulations to identify potential targets to test with existing drugs and even check effectiveness with future COVID variants. So that's a way that they're using computer simulations. Here's another one. It's going slow. There we go. I'm not going to read the article, but just to you, applying computer simulations in battling with COVID-19 using pre-analyzed molecular and chemical data to face the pandemic. Easy. Moving on. Here's one where it says, special report, the simulations driving the world's response to COVID-19. This one was dated, I forget where the date went. Well, I don't know what it's dated. But this is an example of a graph that was made by computer simulations looking at a potential surge that was coming up. This is, what is the date on this? Yeah, so it says 2020. So that was last year. So they were predicting a surge in the virus. Let me look at this one here really quickly. I'm sorry that it's loading so slow. My computer's going slow. Oh yeah, and this one was from February 7 of 2020, so more than a year ago. They used a computer model to simulate how the disease was going to spread around the world. The lines that you're seeing are like people getting on airplanes and then spreading it to other cities around the world. So that's just giving you a sense. We've been using computer simulations, but I wanted you to be really clear that that scientists are using computer simulations, that this is legitimate science, that they use that. Okay, let's go back to where we were and we'll continue with our lesson 3.7 student activity sheet. So part 2, or the second part, says recap, and I'm going to get my image out of the way. Last time we did a simulation that looked at the impact of infecting the buffalo and then introducing a vaccine later. Remember that the buffalo are being infected by the cattle. Remember, humans are bringing the cattle in and the cattle are getting the buffalo infected. And the vaccine is being used on the cattle, but you don't actually see the cattle in the simulation. So the simulation is just showing us what's happening to the buffalo and the wildebeest populations, but it's not showing us what's going on with the cattle. Last time, we made some predictions about how the disease and vaccine would impact both the buffalo and wildebeest wildebeest populations. And I think some of the results might surprise you. So we're going to respond to our questions. So if you haven't already, pull up your previous lesson 3.7 student activity sheet, and we will go ahead and get started. And I don't know where I put my copy of it. I might need to pause this for a second. Give me a moment, because I think this is the wrong copy. Yep, that's the wrong copy. What did I put in, everybody? I hate it when I do this. And now it's all spinny. I might have to pause. Oh, there we go. That's the one I was looking for. Okay, so I have to open it with Cami. I didn't have it ready for Cami yet. So hoping that you're taking a moment right now to get yours open as well, so that I'm not totally wasting your time. We've done the first half. We did the computer simulations. Lots of you did your own computer simulation, and you took a screenshot of it. So this is where you would want to take a look at those screenshots and compare them to the data that I have. Now, I'm going to show you data from 3 different trials. You are invited. It is suggested. I want you to put in your own data for one of your trials, so that you can compare your data to my trial. So give me a second while Cami opens up. We're going to scooch over. So just reminding you, this one's blank right now, but just reminding you what we've been talking about. We'd made predictions, and we said, if you infect the buffalo population with a disease, how do you predict that will affect them? And we said the population will decrease. And same with the wildebeest. We think the population will decrease. Okay, pretty straightforward. We were also wondering and making some predictions about how migration, how the wildebeest migrating were going to impact things. And I think there's going to be some surprises. And then what did you think were going to happen to the buffalo and wildebeest when the cattle start to get vaccinated from rinderpest? And I don't think there's any huge surprises there. So we went ahead and did the simulation, and now it is our job to fill in this information here. And I wonder if I can make this full screen. What happened? Nope, full screen makes my image go away. So I'm going to undo that. I just wanted to make it big enough so that everybody could read it clearly. And then let's make this not 100%. Let's make it 125 and see what happens. Okay, well, that'll work. It's not great, but okay. So the first thing, we want to look at the observations for all 3 simulations. So I'm going to go back here, and I'm going to open up my screenshots from this particular I'm going to open up the screenshots I have from this particular thing. There we go. I did the simulation 3 times, and you can use my data if you want, but I'd love it if you use some of your own data. So which one did I do first? I think this is the one that I did first. I did this one in class. So I clicked on it. It's opening up. And here's our first simulation. And I think, is that the first? Maybe that wasn't the first one, but that's okay. So let's take a look at what's going on here. I just want to remind you, we started with the same amount of buffalo and wildebeest in all the simulations. We started with 10. At about time 500, we infected the buffalo. So that's when you see circles around the buffalo. That's how you know that they're infected, or around the wildebeest. And then at time 1000, we clicked the vaccine, and we made the vaccine work. So then there were not as many cattle infecting the buffalo and the wildebeest. We allowed the wildebeest to migrate, and we allowed seasonal rains. So if you notice, the wildebeest are all kind of bunched together. This is important. The wildebeest are all kind of bunched together, and they're following the rains. As the rains move, the wildebeest are moving back and forth across the grasslands. So now let's go ahead and take a look at actually what happened. So I'm going to see, can I make this bigger? I can. So let's look at this graph down here. At time 500, so even before time 500, right at the beginning, both populations started out with the same number of animals. But notice that the wildebeest increased faster than the buffalo did. So their rate of increase was faster. Remember that they reproduce a little bit faster than the buffalo did. So what was interesting was when we added the disease and started infecting buffalo, the wildebeest population plummeted. Look at how fast. The blue line is the wildebeest population. It just crashed. Now, the buffalo population eventually started to go down also, but nowhere near as fast as the wildebeest population. And so I want us to puzzle over what is going on here. Then we added a vaccine at time 1000, and you can see both of the populations starting to recover then at time 1000. And then there's those normal fluctuations that we get because of the rains and because of competition and, you know, all kinds of things that are factoring in. But it's this that's really kind of a surprising result that maybe we didn't predict, is that the wildebeest would be hit so hard by the disease. And we're going to see if we can figure out why. So now in our notes, and I got to remember where my notes are. There we go. In our notes, we're going to make observations for all three simulations. So for this first simulation, I'm going to go ahead and click. And if you guys could make sure you use a color other than black. What color am I using? I'm using purple right now, and that's perfect. So let's go ahead and write this one. So in the end, so at the very end, which was time 2000, in the end, there were, I'm looking off to the left because I have the results over on my other computer and I can't memorize them. So there were 103 buffalo and 57 wildebeest. Okay, and what other observations can we make? Well, the wildebeest, these are observations. The wildebeest were following the rains. And they were competing. Gosh, I can't spell. It's hard to spell and talk. Competing with the buffalo. So as they move across the Serengeti, they get into the buffalo's territory. And so when they walk through the buffalo's territory, they're competing with the buffalo. Interestingly enough, they are also coming in contact with the buffalo. So if the buffalo were sick first, the buffalo were able to spread it to the wildebeest. So now the wildebeest get it because they're moving through the buffalo territory. Let's see. Then both population, or I'm sorry, the wildebeest were impacted more and faster than the buffalo population by the disease. So they were impacted. I'm going to write more. Sorry. They were impacted by the disease more and faster than the buffalo population. Their population just really fast. And then they both recovered. Both populations recovered after the vaccine. So we saw both populations increasing. Okay, so that's our trial number 1. Now, anytime if you have your screenshot and you want to write, I'll do trial 1 and trial 2, and then you can jump in and do trial 3. I'm going to write my own trial 3 for anybody who was absent or didn't do the simulation. But if you want to write your observations of your trial 3, super good. That's a great way to do it. Okay, so trial number 2. Let me go back, see if I can remember where it is. So this is trial number 1. Let's see if we can get trial number 2. Oh, I clicked the arrow. My computer is just glitchy. It really needs me to shut it down. Okay, so this should be trial number 2. And let's see where we are. So we're at 124 buffalo and 42 wildebeest. Now that's so interesting, right, you guys? Because we started with 10 and 10. We started with 10 buffalo and 10 wildebeest, but look where we are at 2,000 clicks. Those wildebeest, they're just not thriving the way the buffalo are. And the question is why? Like, why are the wildebeest having so much a harder time? Look again at time 500. That's when we introduced the disease. So we see the wildebeest population just crashing. The buffalo population went down. But then at time 1000, both populations recovered again. So we're seeing similar things, so we can make some similar comments. So in the end, there were, I got to look at my notes, 124 buffalo and 42 wildebeest. What should we say? So how about again, the wildebeest were impacted faster and more severely than I'm going to make this fit, than the buffalo population. Both recovered with the vaccine. Remember, the vaccine's not being given to these animals. The vaccine is being given to cattle, but now the cattle aren't constantly reintroducing the disease to these wild animals that never get vaccinated. Okay, I'm going to look at trial number 3. If you want to skip this section and do your own trial number 3, that's awesome. If you just want to stick with me, you totally can. So let me go back to my notes and back to the third trial, and let's see if we see anything different or if we're still seeing the exact same patterns. Just a moment, my other computer fell asleep on me. I had to type in my thing. Okay, whatever. All right, so third trial we end up with, so we're looking at 100 and, whoops, that went, can't see it now, hold on. There we go, 128 buffalo to 40 wildebeests. What happened? Hold on, it skipped around. Give me just a second. Why is my computer being glitchy? I click on it and nothing happens. Okay, 128 buffalo and 40 wildebeest. Something feels funny. That feels like the numbers changed. What did I screw up? I have no idea, but I'm going to go with it. So 128 buffalo and 40 wildebeest. So we will go with that. So let me figure out where we're going to write that. So in the end, that's how we always start these, right? In the end, comma, there were 128 buffalo, and what did I say? 40? 40 wildebeests. And let's just double check and make sure that we're seeing a similar pattern to what we saw. We see the wildebeest increase faster at the beginning, so their population is increasing faster, but then they plummet well below the buffalo population. Remember, the buffalo are a little bit slower about reproducing. The wildebeest are just not recovering well, but then they both recover at time 1000. So why did we do 3 trials? They're never exactly the same, but what we're looking for is a pattern. When we saw that really steep incline from the wildebeest in the first trial, was that just a random thing, or was that really a pattern? Is that something that we're going to be seeing from the wildebeest? Now we've seen it happen 3 times. Let's write about it for the 3rd time. Yet again, and remember, you can always put this in your own words. You don't have to write my exact words. The wildebeest were affected by the disease more than the buffalo. We'll just leave it at that. Both recovered from the vaccine. Those are our 3 observations. So now let's go ahead and make sense of the things that we were looking at. First of all, before we go into the questions, I just want you to think about it. And I wish that we could talk to each other right now, but just what do you suppose is causing the wildebeest to have so many problems? So I want you to think about what makes the wildebeest, and really there's only maybe 2 big things that make the wildebeest really different than the buffalo. The first thing I can think of that they're really different is that they reproduce faster. So that we certainly saw them reproducing faster. Each graph, we saw their population increasing faster. So when the blue line is in front of the brown line, that means they're increasing faster. They're having babies faster. So that's one way they're different. But the other way, trying to remind you of this story, the other way that the wildebeest are different is that they're migrating. They're moving backwards and forwards across the plains with the rains, whereas the buffalo pretty much stay put. They move around a little bit, but they don't migrate with the rains. So is there something about migrating? Look at the wildebeest, everybody. Look at where the wildebeest are compared to what the buffalo look like. Why is the disease affecting the wildebeest so much more than it's affecting the buffalo? Wish we could talk about it because I hate just giving you answers. But do you notice that the wildebeests are really close together? They're super packed together. So we know that disease happens more when individuals are closer together. They're all staying together as they migrate. They migrate together. The buffalo, they're way spread out on the Serengeti, and they don't travel much. So what's happening is when the buffalo first come down with the disease, the wildebeest migrate through their illness, they catch it, and then they just spread it like wildfire through their population because their population stays together. And so they're not maintaining social distancing. Isn't that ironic? This has nothing to do with coronavirus. This unit has nothing to do with coronavirus, but it sure rings a bell, right? Like we can be like, oh yeah, we've heard of that. Whoops, I'm in the wrong place. All right, so let's take a look and see if we can answer these last 4 questions, and then we'll be done. Consider all of the factors you observed in the simulation. What conclusions can you make about how a disease like rinderpest affects the population of buffalo? So let's go ahead and type it. Rinderpest decreases the buffalo population somewhat, but the buffalo don't spread it to each other rapidly because they don't hang out together. How about that? Hang out together. They do a little bit, but they don't hang out like the wildebeest actually hang out in hundreds of thousands of them all at a time. Okay, consider all the factors you observed in the simulation. Same question. What conclusions can you make about how a disease like rinderpest affects the population of the wildebeest? Okay, so now we've got some whole new ideas that maybe we hadn't thought about. That migrating should be good because migrating allows you to follow the food, and so they're following the food. But when it comes to a disease, they're not maintaining social distances, and so that's a real problem. So give me a second. So rinderpest spreads through the wildebeest population rapidly because they are migrating together. So their population is more severely affected than the buffalo population. If I'm going too fast for you, just pause the video at any time so that you can get caught up. You know how to do that. Okay, number 11. During this simulation, what do you notice about the migration patterns of the wildebeest and the pattern of the seasonal rains? So the wildebeest are following the seasonal rains. The wildebeest are following the seasonal rains, which means they're following new growth of plants. How about that? So it's new food for them. Okay, and then the very last question, and then we're done. We can get this submitted today. I'll leave the answers up there so you can see it. Number 12, during this simulation, the seasonal rains were on. How does this affect the populations of both the buffalo and the wildebeest? So in this case, give me just a second here. So whoops, I'm not typing. Hold on, I flubbed that up. The wildebeest are migrating through the buffalo territories, or buffalo, yeah, we'll say territories, so they get infected. Then they spread the disease throughout their own population because they are migrating together. Okay, so hopefully that made sense. We are going to do a summative next week that has to do with this principle of what's going on with these wildebeest and all these crazy factors that are, it's not just immediately obvious that their populations are going to go down. The buffalo population only went down a little bit. The wildebeest population plummeted, and it had to do with the fact that they were migrating. All right, ladies and gentlemen, let me know if you have any questions. Have a good one. Oh, and don't forget to submit. You're ready to submit, so submit that right now. It's due by midnight. Good.